C'est le dernier, celui-là.
C'est le dernier,
Ouais.
merci.
Ok, ouais, pas de souci, t'inquiète.
Est-ce que tu as de la vidéo ou du son?
Non,
Non, que des
slides.
Ok. Donc comme d'habitude, on fait un micro utiliser, ce sera pour le public.
Ouais, normalement, je n'ai pas de questions.
Ok.
Enfin, non, je pense que ce sera assez long. Bonjour.
Tu peux y aller quand tu veux.
Hey everybody. So my name is Guillaume Felley. I'm a developer at Liquidity Network, and today I'm going to speak about off-chain transactions and more precisely off-chain scaling. So this talk is based on this paper from Lewis Guidon, Pedro Moreno Sanchez, Stephanie Rose, Patrick McCurry, and Arthur Gervais. So this paper summarizes the different option and explain what layer 2 scaling is about, and it's made by Solid Academics. So if you want to go more in depth into what I'm gonna quickly present, read this paper. All right. So yeah, blockchain don't scale, and yeah, let's skip the slide. So how can we scale a blockchain, right? So you have basically 4 ways that you can improve on that. You can improve on at the network layer by reducing latency and bandwidth, so that validators can process blocks faster, and therefore blocks can be bigger. You can tweak the consensus, so that some consensus algorithm might introduce less overhead, and therefore you could scale more. You can do sharding by partitioning the network. So here a challenge is that if you do that, you might lose on interoperability. And then last, you have off-chain. So off-chain is basically delayed on-chain settlement. So all this approach are complementary. And yeah, I believe if you want a blockchain that truly scale, you can look into all of them. You will need all of them. In one word, one sentence, off-chain transaction is a transaction outside of the blockchain, but which is still secured by the blockchain. Why is it exciting? So basically, you just need one on-chain transaction to join and one off-chain transaction to leave the network. But in between, you can do as many off-chain transactions as you want that are hopefully secure, and you don't have any latency, and you don't need to pay any fees to the miners. And the last but not least, you have backward compatibility, which means that you can implement this on blockchains like Ethereum. All right, so what off-chain solution do we have? We have basically two families, commit chains and channel networks. So yeah, let's start by looking at channel networks. Very briefly, I will explain how payment channel works. But basically, so here you have a blockchain, and 2 parties set up a channel together. One guy deposits 1 coin into it. Then he can make a transaction off-chain, sending 0.05 coin to the other guy. You have the state that is now updated. The guy on the right has 0.5 now. Yeah, 0.5, and then you can send it back. And then somehow this state here gonna be invalidated, and then you have a new state here. And sometime later, the channel will be closed, and this balance will be settled on chain. All right. So now, how do you make sure that is gonna be the latest state that is enforced on chain, right? So this party here might be malicious and wants to submit the on-chain and close the channel with the old state, the number 1, where he has more money than the latest one where he has less money, right? So basically, you have a dispute mechanism. So either of the 2 parties can start a dispute, and both parties will provide their own evidence, and the blockchain will somehow settle the dispute and choose which state is the latest. And hopefully it will choose the last one. All right. So this works with some state replacement methods that you're gonna somehow invalidate the old state. And yeah, so those are the four state replacement methods that you have, from the most simple to the most complex. So over time, like the payment channels got more complicated. So at the beginning, you had like simple incentives, so one-way channel. So in one-way channel, you don't need any dispute resolution mechanism, because as a recipient of a transfer, you will always submit the latest state unless you are silly and you want to lose money. And then we have seen the emergence of time locks with the duplex micropayment channel paper, and this allows basically for bidirectional payment channels by introducing an expiry time. Then you add like the revocation state replacement, which is the one currently used in the Lightning Network. It uses a pre-image to basically revoke images. And the most recent one is version, which I won't get into detail here, but you can check onto the paper. All right, then you have state channels. Yeah, so those three are like state channels proposals. And on state channels, you can do like game, voting, auction, and so on. But like, you cannot run arbitrary code like you could do on the EVM. Oh. Okay. All right, so synchronization. So what I mean by synchronization, like two parties might not have like a direct relation between each other, so you might need to go through these intermediaries to send a payment, and then you forward the payment through these two guys in the middle. So this is called routing. And what you need to achieve that is a simple conditional transfer. So this three transfer here needs to happen atomically, so either all of them, either none. So there are two techniques to achieve that. One is HTLC, so hash time lock contract. And those allow to enforce that the payment happens atomically. And the second approach is one called virtual channels. So virtual payment channels means that you establish a payment channel with through your intermediaries. So once you set up a channel, you don't need to talk to the intermediaries anymore to make payments. And then you have this network graph. You have to keep a record of like all the channels that are open, and you hopefully have to route through that. You have to advertise your channel and so on. So yeah, so the good and the bad of the payment channels, they are so it requires some collateral, and so each of those ops basically increase the amount of collateral that you need for this payment channel, and that might be expensive, and that makes it not practical for large payments. It's fairly decentralized, at least on paper. You have strong censorship resistance, and you don't need direct connection with everybody that you want to pay. And yeah, it's optimistically fast and cheap, meaning that if your counterparty is not malicious and everything goes all right, it's fast and cheap. But it might not be. All right, so on the other side now, we have commit chains. So the two most well-known commit chain constructions are no-cust and Plasma. Basically, a commit chain, the way it works, you have so-called this server in the middle here, or we call him the operator. And you have these users around. And this operator periodically commits a constant size checkpoint, which is actually a Merkle root. And yeah, the users makes off-chain transaction by talking to the server. After some time, there will be a new Merkle root that updates the state of everybody here with their transactions and so on. And it goes like this until forever. So one important thing is that you have to audit each checkpoint. It means that you have to look at them, that everything is correct and as expected. If it's not, you need to challenge. All right, so this looks like a fairly centralized system, so it's true, but it is untrusted and non-custodial. The operator cannot steal coins or double spend coins or mint new coins. And yeah, and most importantly, like the operator cannot prevent you from leaving this commit chain. Meaning that if you're unhappy or if it doesn't work, you can just leave without asking anyone's permission. What it can do bad is basically censor you, preventing you from making transaction. But the way to get around that is basically to fall back onto layer 1 or to move to a new commit chain that won't do that and that you're happy with. So I mentioned there is Plasma and Nocust. So very quickly, Plasma, you have non-fungible coins. So like in this Miracle tree, at the leaves of the Miracle tree, you have like a single coin that you can't split. So you have to send, like, for example, 1 Ether or nothing. You cannot split them. And yeah. So the second one, which I'm working on, called Nocust, this is account-based versus Plasma, which actually is UTXO-based. And here you have fungibility. So yeah, I'll explain a bit how it works. So now it's specific to Nocust. Yeah, so in Nocust, you have this period here between 2 checkpoints that can be fairly long. Typically on our current version, we do like 36 hours. So what that means is that if I make a transaction now, maybe I will have to wait a very long period of time before my transaction is actually included into the checkpoint and therefore confirmed. So that's not great, right? I might need to wait 20 hours or up to 36 hours for my confirmation. And the way that we get around that is that we have an insurance period. So that means that we provide a pool of collateral that is used to ensure not yet confirmed payments. So what you get out of that is you get basically instant economic finality, because if I make a transfer, in case something goes wrong into the future with this upcoming checkpoint and that my transaction is not included as expected, I can tap into this collateral pool and get my money. So if I receive 1 Ether, I can go to the collateral pool and take 1 Ether from there if the next checkpoint is incorrect. All right. And yeah, so the collateral is reusable each round, so it's fairly efficient. And this way you get instant transaction finality, which is a big improvement over current user experience that you have with blockchain, where you need to wait for transaction confirmation and to be included into a block and so on and so on. Okay, so security properties. You might wonder, like, how is it secure? So let's look at some attack scenarios. First, we have a commit chain, and it's gonna disappear after some period of time. So you have the first checkpoint again after 36 hours. You have 100 transaction in between, then one more round of 100 transaction, and then a few more transaction, and then this operator just disappears. So what does that mean? That means that transactions from 1 to 200 are actually safe because they are committed on chain, and users can withdraw them at any point in time based on that checkpoint. But the transaction from 201 to 230 are not. So they are kind of reverted, which is bad. But there is this insurance pool that users can claim money from to recover. Okay, so now let's look at double spend. So we have Bob Prime and Alice. So obviously Bob Prime wants to send 50 Ether to Alice, and we'll try to send 50 Ether to Bob Prime. And that does not work, and that doesn't work because simply you have the operator in the middle that does accounting, sees that Bob cannot spend his balance twice, so he will prevent that. So that was easy, right? So now more interesting, like Bob is actually the operator. So Bob colludes with the operator, or he is himself the operator. So in this case, you can actually double spend. And Alice won't notice anything at first, but once the checkpoint is submitted, she will notice that something is going wrong. So basically, the data structure that we are using makes it obvious if, like, there is any inconsistencies or if the operator is trying to cheat. So Alice, in this case, will see that there are 50 ether extra in the commit chain that came out of nowhere. So she will open a challenge and the operator will lose. This checkpoint will get reverted and she won't lose anything. Second attack scenario is also simply like the operator tries to make an unauthorized transfer, so transferring money from Alice without her signature. So in this case as well, Alice will quickly notice it in the checkpoint and can open a challenge to revert that. Okay, so commit chains, what are the advantages and the cons? Recipient can be offline when receiving a transaction. So this is kind of nice because like that's what this is the UX you get out of current blockchain transaction now. But if you look at payment channels, for example, you somehow need to the recipient need to countersign. So the recipient needs to be online. I cannot send you money if you're not online. Yeah, so with commit chains, you get limited decentralization, at least from an architecture perspective, and therefore limited censorship resistance, because you have this one single node. Yeah, so it's fairly collateral efficient. You have instant and free onboarding, so this instant onboarding means that I don't need to make an on-chain transaction to join the network. Therefore, here it improves also on the user experience. And last, you have data availability challenges. I haven't touched on that, but you as similar to other blockchain protocol, you have to monitor the chain and react based on if something goes wrong. And here it's about data availability. If like you are missing data to audit your chain, you will have to open a challenge to force the operator to release the data, even though there might be nothing wrong. So quickly, you can do arbitrary smart contract on a commit chain, but we've implemented token swap. So basically, with token swap, it's like the primitive you need to build an exchange. And yeah, so at Liquidity Network, we've built text that is based actually on Nocust. And it is now on testnet. If you want to try out, just go on this link. All right, that's it. So if you have any question or, yeah, happy to. 2 minutes, 3 minutes.
Yeah, thanks for, so I guess the SOK paper was like this kind of overview of, yeah, that's great. Can you go a couple slides back? Like, I'm thinking because I've been, actually, yeah, the one with the good and bad of the commit chains.
Okay.
Yeah, because yeah, this one. So yeah, I've been thinking. Yeah, I spent some time building this kind of commit chain lately, and I'm thinking if it has the same problems like these bad things, it has this feature that kind of similar to Ethereum. Anyone can be like. The validators kind of replicate the work of those who of the operator, right? So you know,
what validator do you speak about?
Oh, right. So
the miners or the operator?
Yeah. Well, I mean, I guess you could compare it to mining, right? But anyone who wants to check that the state is actually correct.
Yeah.
And in that sense, you could swap the operator for somebody else. And I'm thinking, does that ameliorate the centralization and censorship resistance? Because in some sense you can, if you can do the operator's work or replicate the operator's work, then I guess.
So yeah, so like I think I didn't mention it, but like the operator is a single person. He has his own private key pair, and it cannot be anyone that just do the work of the operator. it has to be one single party.
Yeah, no, well, I mean, it's in our construction, it is replicatable, but
Yeah.
of course that comes with a trade-off.
So yeah, like you could have several operators, but it becomes very tricky because of data availability. So you have to make sure that the guy that wants to validate and to create a checkpoint has all the data of all the accounts, otherwise he can't. And you could also like game that the users could like somehow take the commit chain down by withholding data, therefore making the operator unable to make a checkpoint and so on, right? Because the transaction happened off chain, so by definition you don't know what happened. Okay, so I guess thank you.